Next, what we're going to do is start looking at quadrilaterals, but we're not really going to be looking at just random quadrilaterals. That would be shapes that just happen to have four sides. But instead, we're going to be looking at quadrilaterals that we can classify by names, quadrilaterals that have certain properties that go along with them. The first that we're going to talk about is a parallelogram. However, about half of our classified quadrilaterals, all the ones that you can name, about half of them are actually parallelograms by definition. This group is going to include rectangles, rhombuses, and squares. Okay, all of those are actually examples of parallelograms. They do fit the definition that we have for a parallelogram, which is that a quadrilateral with opposite sides parallel, which is kind of an interesting thing about the definition of the parallelogram, because if you really start thinking about the parallelogram, it has a lot of properties that go along with it. Okay, there's a lot of things that we know to be true about it, yet simply the definition is just a quadrilateral with opposite sides parallel. Everything else that we believe to be true about them is actually just considered a property of them. And what we're going to do through these notes is prove those properties are true given this simple definition that the opposite sides will be parallel. All right, so parallelograms have four properties that we're going to be proving in this video. The first is going to be that opposite sides like BC and AD or AB and DC are congruent. By definition, they're parallel, but we're going to be proving that they are actually congruent. The second property we're going to prove is that opposite angles are congruent. Okay, so like A and C and D and B. Prove that those are congruent. The third property is that consecutive angles are supplementary. Oh, I ran out of space there. Let's scoot that over just a little bit. They are supplementary. There we go. For example, A and B are going to add up to 180, and A and D are going to add up to 180. Of course, if B is the same size as D, then that would probably make sense that if these are supplementary, then these would also be supplementary. But we got to prove all these things. Okay, and then for the diagonals bisect each other. Okay, what that means, if we draw a segment from A to C, also draw a segment from B to D, that point of intersection is going to break each of the diagonals equally in half. Of course, the diagonal from B to D is going to be longer than the one from A to C, but where they meet in the middle, they will bisect each other. All right, for example one, let's go ahead and prove that opposite sides of a parallelogram are congruent. Okay, we're going to prove that AD is congruent to BC, and at the same time, we're going to prove that AB is congruent to DC. All right, to start things off here, we don't really have given information other than the fact that this is a parallelogram. Okay, so what I'm going to write down is, for step one, that AD is parallel, that's that top line here, AD is parallel to BC, and I'm also going to write AB is parallel to DC. Okay, and the reason that I can do this is because we do have a parallelogram, and that is the definition of a parallelogram. Okay, so I don't need to write down a given that I do have a parallelogram. Because we do have one, I can go ahead and just start applying the definition to show that. All right, so for step two, what I'm going to do is draw a diagonal. We're going to draw line segment DB. Okay, which is called an auxiliary line. Just anything extra that we add to the picture. Okay, so here's BD. All right, and when I do that, I'm going to identify some angles here. I'm going to call that angle 1 and that angle 2. Okay, and for line 3, angle 1 is congruent to angle 2. These are actually the same size. And the reason that we know that is because BD is a transversal with AD and BC being parallel lines. So angles 1 and 2, under the circumstance that I got the parallel lines, are going to be congruent. We call that alternate interior angles. Likewise, I can call this angle 3, this angle 4, and for the exact same reason, I can say that they would be, which is AIA, I can say that these are going to be congruent. However, there's a little bit of a difference here. Angles 3 and 4 are not going to be based off of AD and BC. They're going to be based off of AB and DC. Okay, but they are alternate interior angles, which will make them congruent. However, I'm going to write down another step first, and then I'm going to come back to that one. So step 4, what I want to do is say that the diagonal that I have right here is congruent to itself. Okay, I want to say that, it's called BD. Let's say that BD is congruent, and on a technicality, I'm going to write it backwards. It's congruent to DB because of the reflexive property. Okay, and then I'm going to come back to angles 3 and 4. Okay, so angle 3 is congruent to angle 4 by AIA, as I had explained that. All right, and by putting in this order, if I go and look back at the picture, let's go ahead and look at this side right here. Angle 1, BD, and angle 3. We've got angle 1 here, we got BD, which is same thing as DB, and you got angle 3. So what I have is an included side between two angles being congruent to two angles in the included side over here. There's your two angles in the included side. Okay, so what I've actually done here is I've created a shortcut, angle side angle, to prove that the top triangle and the bottom triangle are congruent. I have proved that triangle A, let's do ADB, is congruent. So if we did ADB, it's going to be CBD. We've proven that those are congruent by ASA. And if they're congruent, then any of the corresponding parts will be congruent, like AD and CB. And AB and CD. CP, CTC. Corresponding parts of congruent triangles are congruent. For example 2, we're going to prove that the opposite angles of a parallelogram are congruent. Okay, and one approach that we could do is literally to duplicate everything that we did in example 1, but then swap out at the end with the angles. Of course, you would need to end up doing some of the problem twice because you would have broken up angles D and B just to show that A and C would be congruent. And that would mean that you would need to draw another diagonal here to make sure that you show D and B are congruent. A slightly quicker approach at doing this would be to use the proof that we just did. Okay, the opposite sides of the parallelogram are congruent. So for my very first step, instead of talking about the sides being parallel, what I'm going to do is write down that AD is congruent to CB and AB is congruent to CD. Okay, let's put some markings. So double, we got single, we got single. Okay, and I can actually start there because we just proved it. We proved that opposite sides are congruent. That would be opposite sides of a parallelogram, but we know what shape we're talking about here. All right, for step 2, I'm going to go ahead and draw BD again. I'm going to draw that. And I'm going to follow that up with BD is congruent to DB. Reflexive property. Okay, so a little bit faster now, without using the angles, I can actually prove right now that the top triangle and the bottom triangle are congruent by side, side, side. Okay, so there's that reflexive one here. I'll just put 3 marks on it so that you can see it. But we've got our singles, we've got our doubles, we've got the shared side there. So by side, 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 they are congruent. So step 4, we'll do triangle ADB is congruent to triangle CBD, side, side, side. Here's 2 of your S's. That's your third one down there. So congruent by side, side, side. Then step 5, we can at least prove that A is the same size as C. By corresponding parts of congruent triangles. We can do that. Now, as far as B and D proving that they're congruent to each other, we could rewrite some things here. We could reset, we could draw another diagonal here at AC. You still get side, side, side. You would still use CP, CTC to show that B and D are congruent. Okay, so what we're gonna do for 6 is we're gonna make this a lot shorter. Okay, we're gonna go ahead and say that angle B is congruent to angle D, and for the reasoning, we're just gonna say it's the same argument as angle C congruent to angle A congruent to angle C. That way you don't have to repeat all the process, but we could figure out, okay, well, what we would do here is draw the diagonal AC, go through all the same steps again and get the same result, which would be that B and D are congruent to each other. For example 3, we're going to prove that consecutive angles of a parallelogram are supplementary. All right, so we actually have 4 different pairs of angles that we can look at. Consecutive angles are going to be back-to-back, so we could look at A and D together as 180, supplementary. You could look at D and C, you could look at C and B, you can even look at A and B together. Okay, just to give a little bit of direction here, what I will be aiming for is showing that A and B are supplementary. But then the argument would be the same thing for all of the rest of them. So we'd really just need to show that one pair works out. All right, for step 1, what I'm going to do is refer to the very last proof we did, which is that opposite angles are congruent. Okay, angle A is congruent to angle C, and angle B is congruent to angle D. We just proved that. Opposite angles are congruent, at least for a parallelogram, which of course is the shape that we're looking at. Okay, step 2. I'm going to do something here that's very technical and write down that the measure of angle A is equal to the measure of angle C. I don't know if I can squeeze this one in. I'm trying to write it small. Measure of angle B is equal to the measure of angle D. Barely got that to fit in there. Okay, and what I'm doing here is using the definition of congruent angles. Okay, and it's going to be important that I change these into measures and equal signs, because what I'm going to do next is use the Polygon Sum. Okay, line 3, I'm going to write the measure of angle A plus the measure of angle B plus the measure of angle C plus the measure of angle D is equal to 360 degrees. Couldn't quite make that fit on one line there. Okay, but this is the Polygon Sum. We have a quadrilateral. We have 4 angles here. And all quadrilaterals are going to add up to 360, which we had previously proven. So we just call this the Polygon Sum. Or you could just write down quadrilaterals equal 360. Something like that would be totally fine. All right, so step 4, what are we going to do here? We're going to take the information that we have up there in 2. We're going to take this information that A is the same size as C and B is the same size as D, and use some substitution. Okay, I'm going to keep the A. As I mentioned in the beginning, I really wanted to work with A and B. Okay, so I'm going to keep the measure of angle A. That's keeping this right here. I'm going to keep measure of angle B. But when I get here, the measure of angle C, I'm going to substitute in the measure of angle A. And right here, instead of D, substitute in the measure of angle B. And everything is still going to equal 360 because it's an even swap. Substitution. And then, with a little bit of algebra, I can group like terms. I've got the measure of angle A and the measure of angle A. So I've got two of those. 2 times the measure of angle A plus 2 times the measure of angle B is equal to 360. Okay, and we could just call that combining like terms. All right, and then last, with the tiniest bit of space that I have here, if I divide everything by 2, the measure of angle A plus the measure of angle B, so divide everything by 2, take out the 2's, and even right here, divide that by 2, I get 180. I guess that'd be line 6, I forgot. And we're using the division property of equality. And what does that tell us? The measure of angle A plus the measure of angle B is equal to 180. In other words, A and B are supplements of each other. And then you can make the same argument for any other pair that we would have here. Okay, everything in the beginning would be the same. What you would do is just swap out for a different pair here. All right, for our last proof, we are going to show that the diagonals of a parallelogram bisect each other. All right, and to get things started off here, what I'm actually going to do is draw the diagonals. Okay, so we'll let that be step 1. We're going to draw, let's see, AC and also BD. Okay, so let's get those added in here. Okay, and they are going to create a point of contact, which will be important. So that point, I'm going to go ahead and just call it P, just for points. Okay, so we'll call it P. Okay, so the picture that we have set up, what we want to demonstrate is that AP is going to be the same size as PC, and also show that BP is going to be the same size as PD. For line 2, I'm going to acknowledge something that we proved earlier, which is that AD is congruent to CB. Okay, they're congruent because they're opposite sides of a parallelogram. All right, so let's go ahead and mark that. We'll put a little single mark on each of those. All right, what I'm going to do next is use some alternate interior angles. Okay, so for line 3, I'm going to be able to write that angle 1 is congruent to angle 2 by AIA, and at the same time, I'm going to go ahead and write down that angle 3 is congruent to 4 by AIA as well. But you know what? I need to acknowledge one other thing before I can do that, because AIA only applies if the lines are parallel. Okay, so let me make one more statement here, that AD is parallel to CB. Sometimes we leave things out and then we realize we got to add in a little bit more. Okay, so these are parallel to each other because of the definition of parallelograms. All right, and now that I've stated that these are parallel, I do get alternate interior angles, which would be congruent. Okay, so line 4, we can say that 1 and 2 are congruent, and 3 and 4 are congruent. I'll get it right at some point. Angle 3 and 4 are congruent. And you're going to notice I didn't use the sides over here. I can do everything based off of the top and the bottom. Okay, and they're congruent by AIA, because the lines are parallel, of course. Okay, so if we just look at the top and bottom triangles, I can actually prove that they're congruent to each other because I have angle, side, angle, also have angle, side, angle right there. So line 5, we're going to say that ADP, that would be triangle, ADP is congruent. Let's make sure I get these in the right order. So ADP, so that'll be CBP. And the reason again for that is going to be angle, side, angle. All right, so if the two triangles are congruent, that would mean any corresponding parts are going to be congruent. For example, this right here, that segment that's right next to the 1, which is across from the 3, I can say that PD, let's make it look like a D right there. All right, PD right here is going to be congruent, and let's be real careful with this here. It is next to the 1 across from the 3. The 1 is congruent to the 2. Okay, so we're going to be looking at PB. We're going to be looking at PB as the same one that we have there. And while we're doing that one, if these two are congruent, let's go ahead and put double markings. Then the other two, AP and PC, which I'm going to go ahead and write as PA and PC, those two would also have to be congruent. Corresponding parts of congruent triangles are going to be congruent. And what does that prove for us? Well, if you look maybe just at that segment here where you have a diagonal, that side is the same as that one, which means that P does in fact bisect it. And if you look at the other one, oh, let's go ahead and put some triples on that. All right, so if you look at the other one, AC, because AP is the same thing as PC, that means that P is a bisector as well, bisects that segment. In other words, the diagonals do bisect each other here.
Wait, what?